So we also have the other part of this, which is fusion. And for fusion reactions, I want to look at these as well. So fusion reactions, there is something called the proton cycle, which takes place on the sun. This is where we see fusion at its finest. It's been sustaining life here on Earth for quite a long period of time. But there are four reactions that we have to consider. So one of them, the first one of them, is the fusion of two protons. So we have a proton plus another proton, and that's going to give us a deuterium. I'm sorry, that's going to give us a deuterium atom. And that's going to produce also a positron. And a neutrino. And the energy associated with that is 0.42 MeVs. And then we've got the second reaction is that we can take a neutrino and we can take a the deuterium atom that we've, not a neutrino, I'm sorry, a proton or a hydrogen atom and a deuterium atom, and we can fuse those. These really aren't atoms anymore. They're really just the nuclei, because at the temperatures that are required for these reactions to take place, these can't actually exist in that as atoms. And that gives us helium-3, and it produces a gamma photon. And that reaction is somewhat more energetic. It's 5.49 MeVs. And then the last of these kinds of reactions is that we can then have the helium-3, two helium-3 nuclei actually fusing to form helium-4. So we take a helium-3 plus another helium-3, and that's going to give us helium-4, and that's going to also produce two hydrogen atoms, because we've got, since we've got we have another one here, another hydrogen atom, and that would give us 4. That gives us the total of 6, and 4 here. And that produces 12.86 MeVs. Now, since we've got positrons being generated here, there's another reaction that takes place, because there's a whole, this being taking place in a plasma, there's also going to be a lot of electrons around. So the positron and the electron are going to react, and that's going to give us 2 gammas. And that is going to give us the standard 1.022 MeVs. So if we look at the overall reaction, and this is called the proton cycle, if we were to actually look at this overall reaction, we'd find that because some of these reactions require, for instance, all right, we have this reaction producing this, and that going to that, but in order, once we get to the helium, we have to cycle everything around twice to get to the helium, so we have to double that. So some of these reactions we're actually going to have to double when we calculate it. So the second one here, this reaction here, because we're going to need 2 helium-3s, we're going to actually have to run this reaction, this sequence twice in order to complete the, and we're also going to have to run this sequence twice as well, because we need 1 hydrogen, we need 2 hydrogen, we need 1 deuterium for this, but we also need the hydrogen as well. So we run that cycle twice. Then we've got the next reaction, we just run that 1 time, and then we have to do this twice as well. So that means that we have to take each of these energies and double them. So this would be 2.0 12.44, and this one is still 12.86, and this one we have to double, so that gives us 10.89, 10.98 rather, and we have to double that, which is 0.84. And if you sum all those up, you should get 26.7 million electron volts, and that would be that's the energy, the total energy for the entire proton cycle. And that accounts for roughly 90% of the sun's energy output. So it's a highly energetic process that's occurring there. And this is the basis for thermonuclear reactions that also take place on the face of the Earth. And the only way that we've ever been able to do that is actually in nuclear weapons. We can look at that, or we actually will look at that in next week's lecture. So I'm not going to go into that right now. But all these reactions have pretty high ignition temperatures. So there's a certain temperature that you actually have to reach in order to actually get this reaction to take place. And you have to go up to quite a high temperature. The calculated value, which is shown on page 152, which is actually calculated by calculating first the effective Coulomb barrier for the reaction, which is only 1.11 million electron volts. But when you convert this into the energy that's required for this, it's an enormous amount of energy, and the temperature is on the order of 1.3, well, it's 1.3, it's about 13 billion Kelvin. So it's a very, very high temperature. But it turns out that even inside the core of a star, we don't actually see temperatures that high. So there actually are only a very small fraction of that, maybe 0.1% of that temperature. So what that's telling us is, well, first of all, we don't need quite that much energy because we've got particles that are both in motion when this happens. So both of them, their energies would actually combine. That would cut the factor down from maybe 1,000 to 500. And then it turns out that some of the particles, this is like an overall average value. Some of the particles are going to have relatively higher energies than others will. Just in general, some of them could have energies that could be, in fact, one could be as much as 100 times higher than other particles in there, so they still average out. So there are going to be some particles that are going to have energies that are going to be maybe 25% of the needed energy, and the rest of the boost probably comes from quantum tunneling. Since you still can't quite achieve that energy, there is quantum tunneling that actually occurs, and because of that, some of these nuclei actually do collide and undergo these reactions. So it is something that, if that weren't the case, we would not be able to sustain life on this planet. The sun would not be burning hydrogen, and things like the hydrogen bomb would not have been possible. Not that the hydrogen bomb is something that I'm really particularly proud of, but nevertheless, it does demonstrate these processes. Now, in stars, these processes happen all the time, and we've got a section on page 153 that is entitled Stellar Nucleosynthesis, and this is how elements actually get made in a stellar furnace. So for instance, we can see that hydrogen's being converted to helium. Helium can then actually fuse with other nuclei, and we can get higher and higher nuclei out of it. And that's basically what we're looking at here. And there's a reaction that's shown which does take place on the sun, which is that if you fuse a number of helium nuclei together, you can actually make neon. And once you've done that, you can take neon and fuse another helium nucleus with it, and that makes magnesium. So you can see how you can build these things up. In this case, two atomic numbers at a time, just by fusing something with helium. So these kinds of reactions take place, and you go to magnesium, and then you can go to other higher elements as well. but eventually you reach a point where you actually hit a barrier, and that is at iron. So the standard nucleosynthesis reaction that occurs just by these kinds of reactions, once you get to iron, you run into a bit of a difficulty, because you can get up to iron in these what are called S processes. These are slow processes. They involve once you get up to iron, the problem is that iron, you can't really absorb. It turns out that the energy of any trans-iron element, any element that's higher than iron, actually you don't, the binding energy of iron is the most stable of all of the nuclei. If you were to actually plot this out, you would find, and I think, is there one in the book? Did they actually do this in the book? Let me see if they actually have a table that shows this. No, they don't, unfortunately. But if you were to actually look at that, you'd find out that iron is at a low value, where you really can't. It's sort of in the valley here, and you can't. You can get fusion in one direction. You can get fission in the other direction. But once you get down to iron, you really can't do anything with the in terms of fusing it with other nuclei, because the energies are just too high. It's just not possible to do that. So what you have to do, if you want to go to higher nuclides than iron, is you have to use processes that are going to involve neutron capture, and you can use thermal neutrons for that. Or you could use fast neutrons as well. I mean, actually, in stars, it would have to be fast neutrons. So inside a star, you can still have these other reactions taking place, where iron can capture, for instance, can capture a neutron, actually capture a couple neutrons at a time, and it can go to higher elements. So you can see some of the reactions that you can get by doing that. Let's see if they actually show any. Well, they don't really show. I mean, they just tell you in your book that iron captures neutrons, and iron 56 captures neutrons until it forms iron 59. So we can look at that. And iron is 20. I think it's 25 or 26. Let me see what its atomic number is. It's 26. So iron captures neutrons, captures a neutron, goes to iron, that was iron 56, I'm sorry, captures a total of 3 neutrons, and it goes to iron 59. And once it goes to iron 59, then the iron 59 is going to start undergoing beta decay, and so that should go to iron, cobalt 59, nickel 59, I don't know where this stops. Could go to copper after that. Let me see if it actually tells us in here. But it will go to higher isotopes. It probably goes up to nickel, and I don't know whether nickel 59 is stable or not. But then nickel, of course, would be able to capture additional neutrons, and you can build up higher and higher elements. And that works, again, all the way up to, actually up to, you can go beyond lead, you can go up to bismuth. But once you get to bismuth, then you hit another wall. So at bismuth 209, that seems to be the highest. Well, bismuth actually undergoes decay to polonium, so I guess that's not really true. We can get up to polonium then, because bismuth 210, if we form that, bismuth 210 will actually decay to polonium and through beta decay. But the polonium itself is going to go back to lead. So we really can't get beyond polonium at all by this process. And the last stable isotopes that we could make would actually be bismuth. So if we want to make elements that are actually higher than polonium, then we need another process, which hasn't been described yet, which is the R process, that makes heavier nuclides. And this is the sort of thing that really doesn't take place on Earth normally. It's the sort of thing that takes place in, and it doesn't usually even take place inside stellar bodies. We actually have to have enormous amounts of energy in order for this to take place, and it's the sort of thing that happens during supernova formation. So when a star reaches the end of its life, if it's sufficiently massive, it will undergo an explosion in the form of a supernova, releasing incredible amounts of energy. And when that happens, then the so-called S process, which is the slow process of neutron attrition. That's the slow process of adding one neutron at a time, or one or two neutrons at a time. That is overwhelmed now, and you have many, many more neutrons produced, much more energetic neutrons being produced. And in fact, it's actually possible to absorb, see if I have a number here, but it's a big number. I think maybe as many as 8 or 10 neutrons at a time can actually be absorbed in this process. Let me see if it says it here. Well, I think it may be mentioned somewhere in the book, but actually it's during these kinds of processes that we can build up higher, what I would call transpolonium elements, elements like uranium and even elements beyond uranium by that kind of a process. So we really need a lot of energy to do that. This also occurs to a limited extent in thermonuclear devices. When they're detonated, they also can produce small amounts of some of these higher isotope elements, because again, there are enormous numbers of neutrons that are actually being produced. The neutron flux is quite high when those reactions take place. There's one other thing that's mentioned, which is called the P process, which is actually the certain neither the S process, the slow process, or the rapid process, which involves a lot of these neutrons being absorbed at once. Neither of those processes account for certain kinds of nuclides that actually have a high P to N ratio, but are still things that actually are formed. And one of them is xenon 124, and it can't be formed through a neutron to gamma reaction followed by beta decay, because it's actually shielded by tellurium 124, which is the which is actually if that were to if you had any neutron rich element that had an atomic mass of 124, it would undergo beta decay until it formed tellurium 124. And then tellurium 124 can't decay to xenon 124 because it's stable. So because of that, you need another process, which is known as the P process, to actually form this kind of thing. And the way that actually works is that there's other kinds of reactions that we didn't talk about. One of them is actually the absorption. Rather than absorbing a neutron, you can also absorb a proton, and you can also absorb a gamma. So a precursor could absorb a gamma and then emit a neutron. That's one possibility. Or a precursor could absorb a proton and then emit some other photon. One kind of a photon could be emitted from that, and either one of those things would actually give you a higher. Here, the fact that you're emitting a neutron is going to raise your P to N ratio, and here the fact that you're actually absorbing a proton, again, is raising your P to N ratio. So that's a way, those are two ways that you can actually make those. Now to make, section 8.3 on page 154, where it talks about, 8.5, I'm sorry, where it talks about synthesizing unknown elements. This is elements that don't exist naturally on Earth, and we already saw that you can make neptunium and plutonium, and you can make americium and curium, and a lot of these other things can be made just by bombarding some of the previous isotopes with particles, whether they're neutrons in the lower cases, or we have to use energetic alpha particles. For instance, plutonium will absorb an alpha particle and form curium and produce neutrons in the process. And as long as the nuclide can actually be isolated, whatever the target is, like plutonium has a fairly long half-life, we can actually use that as a target, so we can bombard it with alpha particles for a long period of time, and we can use that to make curium, and sizable quantities of curium have actually been prepared. But eventually you get to a point where you really can't do this anymore, because you get to the point where when the nuclei become very, very large, one of the problems is as you get to larger and larger nuclei, you get to smaller and smaller half-lives. And in some cases you've got half-lives that are much less than a second, even less than a millisecond, when you get to some of these really big, super heavy kinds of nuclei. So there's an example that's given here where one of the ways that we can get around that is we can take curium, which we have a fair amount of, and since we can't actually hit it with neutrons, because we would just be making these, we couldn't make a much higher atomic mass element if we just use neutrons, but we can use other nuclei that are larger mass nuclei. And one of the things that's done is that the carbon-12 nucleus can be used. And there is a typo or some kind of a mistake on page 156. The equation that's shown, which says that curium plus carbon, it's supposed to say nobelium, but for some reason it says plutonium. I don't know why, but it should, that reaction should actually read 246 curium, and curium is 96. It's absorbing a carbon nucleus, and that's going to give you a nobelium, which is a considerably higher mass element. Nobelium is 104. 100? No, it can't be 104. It must be 100 and I guess it's 102. And 258 minus 4 is 254, and then you're producing 4 neutrons in the process. So you can actually, four neutrons being made in the process. So you can actually use that as a way of getting to higher isotope elements. It becomes more and more challenging the larger these elements become. There's element number 111, Röntgenium, was actually made by taking bismuth. This is kind of interesting, and accelerating nickel nuclei which are absorbed to give the Röntgenium and produce a neutron. So it is possible to do that, but again, as we're getting up to these higher and higher isotope atomic number isotopes, it turns out that again the half-lives become shorter and shorter until they're getting down into the millisecond range. It is believed, however, that at some point we're actually going to get reach an island of stability. If we can get to a high enough mass, we're going to start to see elements again that have half-lives maybe in the seconds or minute range. So it might be possible to make even higher atomic mass elements that way. All right, thank you again for your cooperation and consideration. And again, I realize it was a long lecture. It'll be broken up into smaller sections. Next week, we're going to look at, I believe it's nuclear reactors and probably nuclear weapons as well.